All right, so our first preliminary question in trying to prove the area of a circle is, what is the integral of cosine squared of x dx? And by the way, this whole stuff that I'm going to present to you is a separate chapter in a lot of textbooks. Usually it's taught in Calc 2, so it's something that you might, if you are doing a rigorous mathematical, science, technical university, they might expect you to have covered this in Calc 2. Some colleges do. They don't all. But it's a common topic for Calc 2. All right, so how do I do integral of cosine squared x? You can play around, try some things. Nothing's going to work except one thing: angle sum identities and double angle identities. So we start with angle sum identities. So these are angle identities that you learn in pre-calc. Maybe you learned these from Mrs. Javier, maybe from Mrs. Who else teaches? I can't remember her name. Anyway, maybe one of the other teachers. So here we go. Sine A, cosine B. I don't know why I can't think of people's names today. Plus cosine A, sine B. You probably learned that last year. And then you probably also, since you were in honors pre-calculus, you went ahead and plugged in, well, what if I do the sum of the same angle? And then it's sine x, cosine x, plus cosine x, sine x, and then what we have over here is really sine of 2x, and what we have really over here is two like terms, so we can combine them. 2 sine x, cosine x. Now this is a useful identity. They used it in one of the Taylor series calculations in the solution in the book. We're also going to need this at sort of a later stage of our calculation for area of circle. One thing I like about it is it really pulls together everything that you could possibly use to do an integral. Anyway, so what about cosine? For cosine, you have cosine of a plus b equals cosine a cosine b minus sine a sine b. Remember these? These are important things to remember. All right, and then also I could, so by the way, I would never memorize the double angle formula. I would remember this one and then be able to derive the double angle formula from it because it's an easy derivation to do. And you can really quickly see what's going to happen here is that I get cosine of 2x equals cosine squared x minus sine squared x. Now, this is the identity that is going to allow us to solve this integral. And we'll see how in a bit. So, but first, with regard to this one, things that we want to keep in mind are some of our other favorite identities, like that sine squared plus cosine squared equals 1, and therefore, sine squared equals 1 minus cosine squared, and cosine squared equals 1 minus sine squared. So these are also all key to doing this type of integral. Not just this integral, but this type of integral. And there's a whole lot of different varieties you can have on this. All right, so now what we're going to do is we're going to plug one of these identities into here. So one easy one to do is, let's replace the cosine squared with 1 minus sine squared. So then I'm going to get that cosine of 2x equals 1 minus sine squared x minus sine squared x. And then I have cosine of 2x equals 1 minus 2 sine squared x. Now, here's what I like about this formula. On one side, I have a square of a trig function, and on the other side, I have a trig function without the square. So in a way, this equation allows us to turn squares of trig functions like this one into things that are just regular trig functions with a linear u substitution that I could easily integrate. So what we want to do is solve this for sine squared. And then I get cosine of 2x minus 1 equals negative 2 sine squared x. So then I can write that as 1 minus cosine of 2x over 2 equals sine squared x. All right, so what I've done here is dividing by negative 2. Since I divided by a negative, I switched the order of these two and then changed the negative to a positive. All right, now, this is our double angle formula for sine squared. It allows us basically to reduce a quadratic trig function to a linear trig function. All right, so what if we do the same thing with, instead of replacing the cosine squared, we're going to replace the sine squared with 1 minus cosine squared. So my cosine of 2x is going to equal cosine squared x minus 1 minus cosine squared x. All right, so that's equal to 2 cosine squared x minus 1, right? 2 cosine squared x minus 1 is equal to cosine of 2x. So once again, what I really like is that here's the cosine squared, like I have up here. I don't know how to integrate cosine squared, but I do know how to integrate cosine of 2x. So this equation is going to allow me to change what I don't know how to integrate into what I do know how to integrate. So I'm going to bring over the 1. I'm going to write the 1 first just so that my construction is analogous to my derivation for sine squared. Equals 2 cosine squared x. And then I have 1 plus cosine of 2x over 2 equals cosine squared x. So these two identities that you get are double angle identities, and they are the keys to doing integrals of this type. So you can see that we can take the cosine squared, we can replace it with something that's not cosine squared, and get something that we would easily integrate, which is our next step.